Okay, we're continuing on here with acids and bases. And last time we talked about a couple of things. We talked about Kw, which is concentration of H plus times concentration of OH minus equals 1 times 10 to the minus 14. We could use this to calculate really either the H plus concentration, which is the acid part of the solution, or the OH minus concentration, which is the base part of the solution. And remember that these guys run opposite of each other. So as one goes up, the other goes down. And obviously vice versa there for each of those. We can compare the concentrations of each of those. And obviously if the H plus is larger than the OH minus, then it's going to be an acidic solution. If the OH minus concentration is larger than the H plus concentration, it will be a basic solution. And if they do equal each other, they both will equal 1 times 10 to the minus 7, which will give you really a pH of 7, and it will be a neutral solution. Remember, you want to make sure you use your exponent button definitely in this chapter. And the smaller negative exponent is the larger number when you're comparing them. We talked about the pH scale, which runs from 0 to 7 to 14. Again, below 7 is acidic, above 7 is basic, and 7 there is neutral. We could calculate the pH by taking minus the log of the H plus concentration. And once again, we talked about your calculator. So if you have a display calculator, again, you're going to punch it in exactly the way it is written. You want to make sure you use your negative button, not your subtract button, which is a common mistake sometimes people will make. Log, and again, put in your concentration using your exponent button. If you have a non-display calculator, again, this one and some of the other ones we're going to see here today, you got to go backwards. So you got to start with the number, hit the log, and then hit the negative button. And that should take care of either of those ways. Any questions on that there? All right, so I think we left off, bless you, with this example. So for each of these solutions, calculate the pH based on what is given to you. So take a few minutes here, see what you come up with. Okay, let's take a look here. So on the first one there, we are given the H plus concentration. So we could go into our pH equation here, minus the log of the H plus, 2.1 times 10 to the minus 5. And that is going to get us minus the log, where my button, there it is, 2.1 to the negative 5. Again, making sure I use our exponent button. Going to give us a pH of 4.68 in this case. Remember, we also talked about 2 significant figures, 2 decimal places is what we should end up with. That would obviously be acidic, as the pH here is less than 7. Any questions on that one there? For number 2, we are not given the H plus concentration. We're actually given the OH minus concentration, which means that we do want to convert it into the H plus concentration so that we can get the right pH. The H plus concentration would be our Kw value divided by the OH minus concentration. And that would get us 1 to the minus 14 divided by 5.9 to the minus 8. Like 1.69 times 10 to the minus 7, I think. 1, 2, 3, 4, 5, 6, 7. Now we have it. We could then go into our pH minus the log of the H plus. And that would get us minus the log here. I'll just take the whole number. And that will get us a pH here of 6.77, which would be slightly acidic. Yes, in this case. Now, if you went straight in to the pH equation by doing that, minus the log of 5.9 times 10 to the minus 8. You did not calculate necessarily the pH, because obviously that is not the H plus concentration, that is the OH minus concentration. So you calculated what is known as the POH, which means you need the OH minus concentration. And that would have gave you a 7.23 POH. That wouldn't necessarily been a bad thing because as we will see, if you take the pH plus the POH, it equals 14. Which means if you then took pH is equal to 14 minus the POH, would get you down to the pH in that case. So as you see, there are some multiple ways that you can kind of get to these things, as we will talk about. Obviously here you can use KW to get the H plus concentration, but you do want to make sure that you are calculating what you think you're calculating. So make sure you're using the right number. Yeah. We use KW to go either from the H plus to the OH minus concentration, back and forth, basically. Yeah. And in this case, we actually wanted the pH, so we could not directly use the OH minus concentration to calculate the pH, but we could either use KW to get to the H plus, which is what we need to calculate pH, or as we will talk about, we obviously could just do what I just did there on top. We could use it to get the POH and subtract 14 to get to the pH as well. Other questions? Okay. All right. So the pH scale is based on the log of 10. So basically for every power of 10 that changes in the concentration, the pH will change by 1 unit. So 1 times 10 to the minus 3 is a pH of 3. 1 times 10 to the minus 4 is a pH of 4. By the way, if you need the pH of something that's 1 times 10 to the whatever, it's the same as the exponent as long as the front number is 1. So 1 times 10 to the minus 5 would be the pH of 5. As we talked about the pH scale and H plus, as the amount of H plus increases, the pH actually decreases. It gets more acidic because there's more H plus floating around in the solution. And obviously opposite of that, as the amount of H plus decreases, the amount of OH minus will increase and it'll become more basic and the pH will start to rise in that direction. Now, there's a couple different ways to measure pH. We did some of that the other day. We have some pH meter, which we didn't use, but pH meter basically does a reaction in here and basically calculates the voltage. And basically it will measure the amount of H plus ions that are floating around in the solution. And you calibrate the pH meter by telling them like this is a pH of 7 and it has a certain voltage associated with it. And this is a pH of 10, has a certain voltage, and it does like a little calibration curve. And based on that, it gives you a nice reading of exactly what the pH is, as opposed to pH paper like maybe you saw the other day. You got to kind of estimate like it's maybe between these two colors, or I can't really tell the difference between these colors. But you can obviously dip it into the solution, sort of match it up to the scale and take a reading as to what you think it will be. Now, we also use litmus paper the other day as well, and it doesn't really tell you pH, but it does tell you whether it is acidic or basic, this sort of solution. And typically, if your litmus paper turns red or stays red, again, it's acidic. And if it is blue or turns blue, it is basic. So again, doesn't really give you a pH value, but is used a lot when you're dealing with acid and bases to give you an idea as to what type of solution you're dealing with. That's the pH scale. And again, we see towards the top here at 14, we got some strong bases. Towards the bottom there towards 0. We have a strong acid. We have some other acids here. Ammonia, cleaners up there in the basic range. Pure waters at 7. If you take some water that's not pure water, it's been sitting out for a while, will the pH be 7? No, it actually will be more acidic, believe it or not, in that range. And that's because it picks up some CO2 from the air and makes some carbonic acid, which increases the H plus concentration, brings down the pH of the actual solution of water. Sometimes people are surprised with, whoa, that's like a pH of 5, and that's the same, right? But especially if you sit out for a while, it will kind of be that way. As we sort of got ahead of ourselves there a second ago, there's a very similar scale to pH, which measures the OH minus concentration. That is the POH, and you calculate by taking the minus the log of the OH minus concentration. It tells you again in the name, POH, you need the OH minus concentration. pH, you need the H plus concentration. And the nice thing about that, as I just showed you there, the relationship between the two is basically if you add it up, it does equal 14. So this gives you some options, as we saw in the last example, that you could, again, just use the OH minus concentration, calculate the POH, and then simply subtract 14, and you will get yourself to the pH pretty quickly, which is a pretty good move. They do run opposite of each other. So the POH scale is also 0 to 7 to 14, but below 7 is basic, above 7 is acidic, and 7 is still neutral. And that is different than the pH scale that we just talked about, where below 7 is acidic, above 7 is basic, and 7 on the nose is neutral. So if you have a high pH, you'll have a low POH. And if you have a low pH, you'll have a high POH. You should always, probably in always case, look at the pH value to determine whether or not it is acidic, basic, or neutral. That is the scale most people have in their head, and that is probably the one you should always look at to determine that. As I mentioned the other day, there is only one answer to that question. It cannot be acidic and basic at the same time. It cannot be acidic, basic, and neutral at the same time, I don't think. So it should either be acidic, basic, or neutral. And very commonly what people will do, they'll calculate the pH and go, cool, it's above 7, it's basic. Then they'll calculate the POH and go, oh, it's below 7, it's acidic, and give both answers. Yes, so again, it's got to be the same answer, it's the same solution, so it can't be two different type of things. Adding to our list here of equations, obviously we have our KW that we saw. We can calculate the H plus concentration if we have the pH by taking the inverse log of the negative pH. On most people's calculators, when you hit inverse log, that pops up to 10 in the caret. They want to do negative pH. On most people's calculators, that's the top left corner there. The shift or the second button and the log button. We'll do that. You could also get the OH minus directly from the POH by doing the same calculation, inverse log of the negative POH. Once again, that will get you negative POH up there. So those are good ways that if you have the pH or the POH, you could get to the OH minus concentration or the H plus concentration. And then obviously you could calculate what you need. Any questions on that there? So again, to do the inverse log, most people's calculators, the second button, the shift button, and then your log button that probably has something that looks like that. We'll do that inverse log. Unless you have a calculator like mine, which has a dedicated button for that, you got to hit it twice to get there. All right, so let's take an example of these two. Why don't we do everything here? Let's calculate the pH, the POH. Let's also calculate either the OH minus in this case as well, and the H plus. And is it acidic, basic, or neutral? All right, grab your calculator, make sure it works. Take a look and see if our calculators are working good. So we'll start with the first one here. I do have the H plus concentration, which means really, since I'm looking for everything, I have two options. I could go right into the pH. I could also use KW to get to the OH minus concentration if you wanted to. I'm going to go actually into the pH equation first. So that's going to be minus the log of 3.6 times 10 to the minus 9. Again, I'm going to punch that in correctly using my exponent button. And that will get me a pH of 8.44. Once I have the pH, I could use the relationship that we just saw that the pH plus the POH is equal to 14. That means that the POH here would be 14 minus 8.44. And that would get me a 556, I believe. At this point, again, I could go back to KW if I wanted the OH minus concentration, or I could use the other formula we just saw. Now that I have the POH, I could get the OH minus by taking, again, the inverse log of the minus POH. Again, on your calculator, that's going to be like a 10 and a caret probably, negative 556. And if I do it there, will get me something like 2.7 times 10. 1, 2, 3, 4, 5, 6, negative 6. And it does need molarity after it, as it is a concentration here. Also, my POH had 2 decimal places, which means my concentration going backwards has 2 significant figures. So again, you want to do the same going each way that we talked about. This would be acidic, basic, or neutral. This guy's going to be basic, as we have a pH above 7. Any questions on any of those there? All right, looking at the second one there, we actually are given the OH minus concentration. So again, here, since we're looking for everything, we could go into KW to get the H plus, or we could just go right into the POH equation, which is that's what I'm going to do. So I'm going to go POH is equal to minus the log of the OH minus concentration. That again is going to give me my POH, which in this case is going to be 1.04, it looks like. Once again, once I have the POH, I can figure out the pH by simply subtracting 14 from it, which is, again, that relationship up here. And if I do that, that will give me a 1296 in terms of the pH. And lastly, I could again use KW if I wanted to get to that H plus, but I'll do this new calculation as well. Since I do have the pH now, the H plus concentration would be the inverse log of the negative pH. So negative 1296 in this case. That again will give us something that will look like this on our calculator. And if we do that, it looks like maybe 1.1 to the minus 13, I think. Times 10 to the minus 13. Again, that would be molar in this case. This guy would be basic here as well, as the pH is above 7. Any questions on any of those? Again, you could also use KW to get to the H plus. Again, with rounding, should come out about the same, maybe slightly different, but you should get there as well. Any questions on any of those calculations there? All right, let's try a couple more here then. All right, so let's just do, let's get that one actually. Let's do this one. What is the pH of a solution that has the pH of a solution is 3.14. What is the H plus concentration? So just calculate the H plus there, see what you come up with. Okay, so in this case, once again, it does tell you what you could get from it. Since we are given the pH in this case, we can directly from that get the H plus concentration by doing our inverse log of the minus or negative pH. So putting that into our calculator, once again, will kind of pop up usually like 10 and a caret and negative 3.14, going to get us 7.2 times 10 to the minus 4, I believe. 1, 2, 3, 4. And again, we'll put molarity on this. Here again, we had 2 decimal places on our pH value. That should in turn give us 2 significant figures on our concentration. And obviously this would be acidic here as the pH is 3.14. Any questions on that one there? All right, one more here. We have the POH is 5.67. What is the OH minus concentration? Okay, so again here, it does tell you what you could get from the POH. You could get the OH minus concentration. And again, that's going to be the inverse log of the negative POH. On your calculator there should pop up something like this. And once again, to punch it in on most people's calculators, the second or the shift button, the log button, the negative button, and 5.67 will do it on most people's calculators. And if you do that there, that will get you 2.1 times 10. -6, I think. I counted right, hopefully. 1, 2, 3, 4, 5, 6. Yep. Molar. Any questions on that calculation there? Obviously, if you have a non-display calculator, you do need to go backwards. So if you have a non-display calculator, you would do 5.67, hit the negative button, then hit the second log, and then you'd be okay. So kind of go backwards on this one as well. Any questions on how to calculate H plus OH minus pH, POH? This, by the way, would be a basic solution. As we subtract 14 there from our 5.67, we got definitely over 7. It would be basic. Any questions on how to calculate any of that there? Okay. So up to this point, we've sort of been given really just generic H plus OH minus concentration, but you may be actually given like a actual strong acid and ask what is the pH of it. Remember, we have a list of some of our strong acids, and those guys are hydrochloric, are nitric, are sulfuric, are perchloric, are hydriodic, are hydrobromic. So these are our really strong acids. Because they are strong acids, when they go into solution, let's say we had something like hydrochloric acid, and let's say the concentration was 0.1 molar. Because it's a strong acid, it will 100% break apart into H plus and Cl minus. And 100% of what you have in that solution is those things. In terms of the pH here, it is the H plus concentration that is the most important. And as we talked about when we talked about concentrations, it is a 1-to-1 relationship between these two, which means the concentration of the H plus would be 0.1 molar as well. By the way, for the chloride, it is also would be 0.1 molar as it's a 1-to-1 relationship. But for pH, that's really what we need, which means we could just go into our pH equation at this point, 0.1, and that will get us our pH value for this guy of 1.00, which definitely is acidic. I would say in the case of us, if you see an acid that's one of those strong acids, pretty much that will be your H plus concentration, which means you can't go directly into it. You can also have a strong base, right? Like this. And if we had a strong base, it also would break on an hydroxide ion. And let's just say we had 0.1 molar for this guy. In this case, it's actually the hydroxide ion that's kind of important to get us to pH. It is a 1-to-1 relationship, which means the concentration of the hydroxide here would be 0.1 molar. That would allow us to calculate not the pH, but the POH from that, minus the log of 0.1, going to give us a 1 for our POH. But then we could subtract 14 from it and get our pH, which will equal 13 in this case, which is definitely basic. So even with a base, if it's a strong base, because it will, again, 100% break apart, you could get the hydroxide concentration, and that could go into the POH, and then you could subtract 14 to get to the pH. Any questions on that there? All right, so why don't you try one here? What is the pH of that one? And what is the pH of, we'll do the same guy here, 0.25 molar. We'll do a calcium hydroxide solution, which is, we'll consider it a strong base. All right, so do both of those, see what you come up with here. Okay, let's take a look and see. So this is a strong acid, which means it's going to 100% break apart into ions. And you'll get your H plus and you'll get your perchlorate here. So this is 0.025 molar. It is the H plus that's important. It is a 1-to-1 relationship, which means that the H plus concentration here is going to be the same. The pH then would be minus the log of 0.025, and we'll do minus the log here, 0.025. Going to give us a 1.60 as our pH, which is acidic. Any questions on that one? Looking at this one, which is a base, the second one, also, if we consider it a strong base, it will completely break apart into a calcium ion and 2 hydroxide ions in this case. This concentration is 0.025. The hydroxide is important here. It is a 1-to-2 relationship, which means we do have to adjust the concentration here of our hydroxide because it's twice as concentrated in terms of it. So we do have to times it by 2, like we talked about with concentrations, gives us an appropriate concentration of hydroxide of 0.05 in this case, as it is not a 1-to-1 relationship. That gets us to our POH, which is minus the log of 0.05 and a 1.30. Again, that is the POH, not the pH. So we still need to then subtract 14 from it to get us to the proper pH. And that would get us 12.70. Which is basic and does make sense here. Yeah. So again, if you thought perhaps the 1.3 was your pH, it shouldn't make sense as this is a base, and that clearly would be an acidic pH. I would say in most cases, if you see something that's a formula for acid or probably bases for our cases, you could probably consider it strong because weak acids is a much longer calculation and weak base is a much longer calculation that you do when you get to 1B. So probably for most cases, ours will probably be a strong acid or base if it's sort of given to you. Any questions on that there? All right, to finish up this chapter here, we're going to talk about buffers. Good talk. No, let's talk about buffers. So buffers are solutions that can resist changes in the pH, even when you add more acid or base to it. So they're able to resist really big jumps in pH, even if you add more acid or base to it. They are not a neutral solution necessarily. So sometimes people think it has to be a neutral solution to be a buffer, and it's not. You could actually make a buffer at any pH you like, acidic, basic, neutral. It just means that whatever pH it is at, it will be able to basically stay there as you add more acid or base if you make your buffer correctly. Some of which you saw the other day when you added 400 drops, right? And that thing finally changed colors maybe when you had your buffer going on there. The reason it's able to do that is because it's able to have two things in there. It needs to be either a weak acid and the salt of its conjugate base, or it can be a weak base and the salt of its conjugate acid. You cannot have a buffer that is made up of a strong acid or a strong base, and that is because it will not set up an equilibrium. So a weak acid and a weak base are weak electrolytes, which means they will be able to keep both of those things in the solution to begin with. So for example, if we take a acetic acid, sodium acetate buffer like you used the other day, that is a weak acid and really is conjugate base. What makes it the salt of its conjugate base is there's a sodium there basically. But the buffer part is really the acetic acid and the acetate part. And those guys are related to each other by the Bronsted-Lowry definition of just 1H plus difference. It's basically the only difference between those two. So when we look at this, what happens because this acetic acid is a weak acid, when it goes for a swim, it will set up this equilibrium that will contain basically both of these things in solution. You have really an acid part to the buffer, and you have a base part of the buffer, and they're able to stay in the solution at the same time, which is really important for it to be able to work correctly. If you try to make it with like HCl and sodium chloride, when you put HCl in there, you will not have any more HCl. You basically will have chloride ions and H plus ions. So you'll only have a base part, no acid part in there to be able to act as a buffer. So that's why something that is a strong acid or a strong base cannot be a buffer because only weak things are weak electrolytes. They're able to keep both the acid part of the buffer in there and the base part of the buffer in there. And that's essential for how it's able to work. So let's talk about how it actually does work. Let's take water, which is not a buffer to begin with, and see what happens. If I add hydrochloric acid to water, it will 100% break apart, as we've talked about, into H plus and Cl minus. Which means in that solution, when I dumped it in there to the water, I just generated a bunch of H plus and some Cl minuses, right? The concentration of H plus in this case, free H plus, has just went up, which means the pH should then do what? Go down. So because we just introduced into this water, which is not a buffer, a bunch of free H plus, we will see the pH jump down a lot. Like probably what you did in the lab, you had like maybe one drop, it went crazily down, or change units. It might go from like a pH of 7 down to like a pH of 2 in that case, a really big jump in the pH because we introduced a lot of free H plus. If we add sodium hydroxide to water, it also will 100% break apart into a sodium ion and a hydroxide ion. And in this particular case, when we do it, what we just did is add a bunch of sodium ions, but more importantly, we added a bunch of hydroxide ions that are freely floating in that solution. And what that did is it increased the hydroxide concentration, which means that it will decrease the H plus concentration. And that means that the pH will actually shoot up in that case, because we have a lot of free floating OH minus. So again, your pH may go from 7 to like 12, 13, a big jump in the pH. And it's because really water is not a buffer. It can't handle the addition of those things into that solution. So what happens if we take a buffer like we did before, everybody's favorite example, which is the one we use, acetic acid and sodium acetate, which is a buffer. And again, that's a weak acid. That is, again, its conjugate base. So when we add our HCl, like we did before, to this buffer that has our acid and our base part in there, the HCl will actually react with which part of the buffer, the acid part or the base part? It will react with the base part of the buffer. It's an acid-base reaction, right? So what will happen is the HCl will find the base part of the buffer, which is sodium acetate, and it will produce some acetic acid in a double displacement reaction. And some sodium chloride in this case. So it produces a couple of things here. It actually produced the other part of the buffer, which is commonly what happens. So as you use part of the buffer, it will always make the other part of the buffer. And that means it's not going to screw up the pH because it was there to begin with. We also made sodium chloride, which is a neutral salt, which won't mess up the pH. But it's actually what we don't see here that we did see with the HCl and water. What do we not see here that we did see on the previous page there with the HCl and water? And that was the H plus being formed. So where to go? There we go. When we added the HCl to water, we made a lot of H plus really quickly. In this case, we did not make any H plus. So what happens is no free H plus was made, which means the concentration of H plus stays relatively constant. And because the H plus concentration stays relatively constant, the pH will stay relatively constant as well. I say relatively constant because if you had a pH meter in that solution, you would see it go down a little bit. So maybe it starts at 7 and goes down to maybe like 6.9 or something like that, but it will not be a giant jump downward because we didn't produce a lot of H plus in this type of reaction. And to finish it out, let's just finish talking about what would happen if we added sodium hydroxide to this buffer. If we did, because this is a base, it will actually react with the acid part of the buffer. and it will do a double displacement reaction where water will be made and sodium acetate. And once again, here we made water, which will not mess up the pH. We made sodium acetate, which was part of the buffer to begin with, which will not mess up the pH. And once again, here it is actually what we do not see that we saw with water, and that is there is no OH minus being formed in this case. So when we add that sodium hydroxide in this case, we end up with no free OH minus, which means that the concentration of OH minus stays the same. And because H plus is related to that, the H plus stays relatively constant. And that also would mean that the pH stays relatively constant as well. So really the way a buffer works is because there's an acid part and a base part to it. When you add additional acid or additional base to the buffer, it prevents the formation of free H plus, which is what you would get when you add more acid, or free OH minus, which is what you get when you add more base. And because it keeps those guys out of the solution in their free form, it's able to keep the H plus concentration relatively constant, and that will maintain the pH relatively constant as well. In the case of the base here, we would see the pH go up a little bit, but there would be no big jump in pH. Maybe it went from 7 to like 7.1 or something like that, but it won't go from 7 all the way up to like 12 or anything like that. So by preventing the formation of H plus or OH minus freely in the solution, it's able to maintain the pH. Any questions on that there? All right, we'll lay it up there, I think.